Hi all, welcome again to another review session video on bounds. In this video, we'll be covering Markov's and Chebyshev's inequality, and we'll be leaving out the Chernoff bound, because Chernoff bound, while it's a very interesting bound, is more or less an application of Markov and Chebyshev, and at least for the purposes of CS70, we didn't think it's as important. But of course, there's the entire notes on it, so we definitely recommend that you take a look at it. So, bounds. Let's go over it. We first are going to go over Markov's inequality, which says probability x greater than alpha is less than or equal to expectation of x over alpha, where this happens for all alpha, such that alpha is greater than 0, greater or equal to 0. But let's actually go over the proof for this. And the reason I want to go over the proof for this is because it's probably the most elegant proof that I know of. And it's definitely my favorite one. So, just because I like it, let's go over it. Apologies if you do not like it, but I think you're in for a show. So, Markov's inequality says, let's just write the Markov's inequality down. First, I'm even going to give this a strong theorem. Markov. Because I think it deserves a theorem, right? I think it deserves it. It says, for all alpha greater or equal to 0. And by the way, if you're interested in this at all, Markov's actually provides perhaps the foundation for all very interesting concentration inequalities. So not just Chernoff, it gives you interesting inequalities like Heftings, sub-exponential, sub-Gaussian inequalities, all the good stuff that you'll learn about if you're interested, because these only really come out at graduate level courses. But these provide Markov's is at the foundation of this. So something as simple as Markov is at the foundation of these ideas. Just something cool if you're interested. Expectation of x. Now I'm using this notation of expectation of x. Don't get too afraid. It's just another way to write expectation without using these square brackets, because using square brackets can sometimes be a little cumbersome. Now, it's a theorem. Let's give it a proof. So, for a proof, we actually start this Markov's from the expectation, and there's a couple really smart things that you do, and I'll point them out as we go. So once you remember the really subtle yet elegant, simple ideas, if you remember them, you'll be in Markov God. You'll be at the level of Markov. So let's start with expectation. You just have to write the expectation down. I'm gonna use the integral notation for this one because I think it's easier. If you're doing discrete, it will be a summation. But do note that when you go into the depths of probability series, actually integration and summation turns out to be the same thing by measure theory. So essentially what we're doing here is correct. But you can do the same thing for summations. I'm just going to use integral because I think it just illustrates a little better. So let's write this down. dx, where notice the f of x, this represents the, in this case, the probability density function for random variable x. Perfect. Now, the first smart thing that we do is we break this down. Well, actually, before we break this down, we're just going to say that this is equal to this. Since x is greater than 0, this is the assumption that we have. This is, yeah. And apologies, I forgot to put this part in. non-negative random variable x. Okay, and because a non-negative random variable x, it sort of implied that alpha should be greater or equal to 0. Okay, so let's take this a little further. So x is greater or equal to 0. We're gonna be doing a really smart thing. This is the first smart move that we make. First really smart move is to say that alpha, we can break this down into two pieces. The first piece goes from 0 to alpha plus goes from alpha to infinity. So I'm going to give this a star because this is really smart. This is a very smart idea. Such a simple thing, but perhaps the smartest thing that you could do. So this is the foundation for this inequality. Okay, now this is the really smart part. We're going to say, oh, you know what? I'm just going to say, I'm going to put a bound to this. This is the second most smart thing. Actually, if I can, I'm going to put a star to every part to this equation. But let's put a star here. Let's remove that star. That's fine. Actually, this star sort of goes for both of these. But what we're going to say is, okay, this is greater or equal to alpha, going from infinity, x times f of x dx. And I hope you can see why. Because this part is, is going to be greater or equal to 0. That's going to be greater or equal to 0 since we know that x is non-negative. So whatever we add to it, it's only going to be bigger than this value that we have right here. It's going to be bigger than this. This entire expression is going to be bigger than this. Again, we know that since dx is greater or equal to 0, because x is non-negative random variable. Okay, that's really smart. Now we're going to do an even smarter thing right here. So notice that this value of x, this sort of ranges from alpha to infinity. This goes from alpha to infinity, right? So what we're going to be doing now is we're going to say, you know what? This goes from alpha to infinity. Let's just do this. Let's bound this even more. So what we are essentially saying here is we're going to be ignoring all this alpha plus 1, alpha plus 2, all the way to infinity. We're going to be ignoring all that, and we're just going to put this bound that's alpha. Super smart. It almost seems like you're taking out so much things, you're taking out so much possibilities for this integration because you're removing everything that's beyond alpha. But this turns out to be perhaps one of the smartest things you can do with this Markov bound. And this is a very common trick that you make when you try to make new bounds, when you try to prove new bounds, is to make all these ridiculous inequalities happen. Notice that here, you can just remove it. You can just take this alpha out because alpha is a constant that's not dependent on x. And then notice that this portion is the CDF going from alpha to infinity. So this represents x is greater or equal to alpha. So this is alpha times probability x is greater than alpha. Ooh, and look at this entire beautiful equation, which seems to suggest that I'm going to divide both sides by alpha, and I get probability greater or equal to alpha is less than or equal to the expectation of x over alpha. What a beautiful equation. I just had to show this to you. So again, there's some really smart things, two very smart things in particular. Let's make it 3. So the first thing is breaking apart into 0 to alpha and alpha to infinity. Second part is getting rid of this entire part. It's saying, okay, we don't care about it. The third part is saying we don't care about this x, we're just going to be alpha. And there you have it, Markov's inequality. So I spent quite a bit talking about this because it's my favorite proof ever. And also I think it illustrates to you from a, and it's going to be very important for you moving on if you ever want to prove more about. Perfect. So warm-up question. This is a warm-up question. We do have a more intricate question right after this, which I'm going to be skipping over because it still uses the same ideas as this one. And once you understand this warm-up question, you can solve the other one with more ease. So I'm going to be skipping over that one. I'm going to be going through this one. Warm-up question. A coin is weighted so that its probability landing on heads is 20%. Suppose the coin is flipped 20 times. Find a bound for the probability it lands on heads at least 16 times. So here, the main idea here is that we want to find a bound for a probability it lands on heads at least 16 times. So this is going to be like probability of x is greater than equal to heads. You want to find that where x represents landing on apologies, not landing, but flipping coin 20 times, and h represents lands on heads 16 times. Number of times it lands on heads. Right? So those are our two events. So let's actually walk through this. I'm going to be going over this part. Actually, let me not go over this one. I'm going to be using this section that I defined. I'm going to take this, make this smaller so that we have a note of this. So this is what we're looking for again. Probability x greater than equal to h. Let's go over it. So probability x is greater than h. So x is the number of times it lands on heads. Once you flip the coin 20 times, h is landing on heads 16 times. You could probably just write 16 there too. Let's actually write 16 to be consistent with the solutions. 16. Notice that this is less than equal to the expectation of x over, over alpha, which is 16. The expectation of x is, because we are flipping the coin 20 times with probability landing on heads 20%, this is a binomial of 20, 0.2, and we know that binomial, the expectation is just n times p. And it also makes sense intuitively because you flip the coin 20 times with probability landing on heads 20%. Once you flip it 20 times, you expect it to land 20 times 0.2 times, which is exactly 4 times. So you expect that to happen. 16 is equal to 4 over 16, which is 0.25. Perfect. So there we have it, 0.25. Okay, let's move on beyond Markov to Chebyshev's. So Chebyshev's, we usually call this a stronger bound compared to the Markov because variance of x term. The variance of x term, remember, looks like that. Is expectation x squared minus expectation x whole squared. And because we are using this extra information of expectation x squared, so this information is already used by Markov, but this is new information that we have. It's a new order term that we have. and it's very useful information. So typically speaking, Chebyshevs tends to be a little more powerful compared to Markovs, but not always. Not always. There are some counterexamples where Chebyshevs is not as powerful as Markovs. And you can read all about them online. So I'm not going to go through a proof for this because the proof for Chebyshevs is just the application of Markov. So again, as I mentioned, Markov is the basis for all these. Alright, so let's go over it. Let's go over the first question. And the only question, which is on using Chebyshevs to derive some kind of confidence interval. So you may have seen this type of question on discussions and homework, and this is just an application of Chebyshev's bound. A more interesting application compared to, say, a question like this warm-up question. So I'm pitching a latest app to a local VC. Any CEO knows the amount of VC invest depends on the level of confidence when I'm pitching. Just depends on how prepared I am. Say prepare a week ahead was probably 8%, and night before was probably 20%, resulting in high and low confidence respectively. So it was probably 80%. I'm gonna have high confidence. Night before, I'm going to have low confidence, was probably 20%. After surveying the data, you learn that high confidence pitches average $4 million, while low confidence pitches net $1.5 million on average. Well, that's quite a bit for low confidence. Both a standard deviation of $0.25 million distributed normally. Use Chebyshev to find a 98% confidence interval for the amount invested. Let's leave out the two significant figures part. Okay, so a disclaimer that I'm going to make here is that we can actually derive a stronger bound than Chebyshev's because we know that this is Gaussian, that this is distributed with a normal distribution. And you may have seen the number 1.96 a lot of times. This 1.96 is used for finding a 95% confidence interval for Gaussians. You can read all about it online. But I just wanted to make a disclaimer that this is not the most powerful thing we can find. You can definitely find more powerful confidence intervals. More tight confidence intervals, I should say. Okay, you're trying to find a 98% confidence interval for the amount invested. So let's first discuss what's confidence interval. What does it mean to have 98% confidence interval? Now, confidence interval looks something like this. It looks like a value x1, x2. And what 98% confidence intervals means, so say that's our 98% confidence interval, it means that we are 98% confident that our value is going to fall between x1 and x2. We're 98% confident. So what does it mean to have 90% confidence? It means that with probability of 98%, it's going to fall between x1 and x2. Interesting. Now, that's not the most precise definition for confidence intervals, but it gets you pretty far. Okay, so between x1 and x2, we are 98% confident, there's probably 98% that our value actually falls in there. So this question is very, very interesting. And I'm going to visualize it for you. So our mu gamma is 1.5, our mu p is 4. And notice that, these two are distributed, these two have some overlaps, like there. And this is very interesting because it leads us to think that we just need to find out where we are 98% confident that it's going to lie somewhere here. So, perhaps something like that in there. Yeah, it seems like 98% of the times it's going to lie between, somewhere along there and somewhere along there. Perhaps even shorter. But this is a geometric point of view of looking at this. So geometrically speaking, our values are going to be, somewhere along here, and somewhere along here. Actually, it goes all the way from 0 to infinity because Gaussians extend to infinity. But it seems like on average, if I take these two values, for example, it seems like this entire area over here will add up to 98%. Okay, let's use Chebyshevs to figure this out. Now we're going to be using a very smart trick here. If you want a more simple question on this, look at discussion worksheets. But this one's a little more complicated because we had two distributions compared to one. We just want to expose you to more problems. Okay, so let alpha be the area under that. Let beta be the area under that. Then alpha plus beta is the total area. That contains 0.98% of alpha and 0.98% of beta. Now, so this is the most important part, in my opinion. We find the 96% confidence intervals, not 98%. So notice that not 98%. Why? Because that leaves 2% off on each tail. So 2% off, 2% off. Right? But the tails which are in the middle are not even taken into calculation. Okay, so let's go through this. Now we want the probability such that we have x minus mu gamma greater than alpha, and we take 0.25 because that's the variance. That's the variance of x squared over alpha squared, and this alpha is what we're looking for. Now we want this alpha to be 0.04 because we are looking for a 96% confidence interval. Now because we are looking for a 96% confidence interval, we are going to say, okay, this is our calculation for that. So we have 0.25 squared over alpha squared, 0.04, multiply both sides by alpha squared, and divide both sides by 0.04, and we get us to this number. Alpha is equal to 1.25 approximately. Right? In a test exam situation, my recommendation would be just write something like this: 25 squared over 0.04 square root, right? And that should get you to about 1.25. Now notice that for a confidence interval, we are going to be calculating confidence interval for gamma and p, gamma and rho. Yeah, I think that's a rho. So for both gamma and rho, we get 0.25 to 2.75, 3.75 to 5.25. So if I can draw them. So again, this is why I'm saying Chebyshev is not the most powerful. If I can draw them out, so it's going to be going from there to 2.75, just about there, and 3.75. Not 3.75, apologies. This is a mistake in ours. This should be a 2.75. 2.75 to 5.25, somewhere along there. So this is the distribution. This is the CI for gamma, and this is the CI for rho. And we just find a union of them. And the union of these two are going to go from 0.25 to 5.25. And that's our confidence interval solution. Now, this is more complicated than usual. So in a usual question, you're not going to be combining two distributions. You're just going to have one, which makes your life a little more easy. But I think the most important takeaway you should have is this calculation. So this variance of x, and figuring out that you actually want the probability over here to be less than or equal to 0.04. And the way to calculate that is by using Chebyshev's. Perfect. So I hope you've enjoyed this video, and I hope you learned a lot about bounds, and I hope you share the same passion as I do on Markov's inequality, which is perhaps the most beautiful equation out there in the world. So I hope you've enjoyed it, and I'll see you in the next video.